In the last lecture, we have discussed about irradiation, total hemispherical absorptivity, reflectivity, and transmissivity. So I am just going to revise all these terms once again. So what is irradiation? It is basically total hemispherical irradiation. Till now we were only talking about irradiation, but basically it is total hemispherical irradiation. The irradiation or total hemispherical irradiation is the total radiation energy incident per unit area per unit time over entire wavelength from all directions. So when I say entire wavelength, it means total. And when I say from all directions, it means hemispherical. And it is denoted by G and is measured in watt per meter square. Similarly, when we talk about the total hemispherical absorptivity, its symbol is alpha. Total here means lambda varying between 0 to infinity, and hemispherical means all directions, and absorptivity means the incident energy which is absorbed by the surface from all directions and over all wavelengths is total hemispherical absorptivity. When I say reflectivity, it literally means total hemispherical reflectivity. So once again, total here means lambda is varying between 0 to infinity, and hemispherical means from all directions. And reflectivity is whatever is the incident energy over a falling over a surface, which what part of it is reflected. So here we are talking about once again total, which means for all wavelength ranges or entire wavelength range, and hemispherical means from all directions. Transmissivity. When we say transmissivity, it means total hemispherical transmissivity. Total once again means here lambda varying between 0 to infinity, and hemispherical means all directions. And we are talking about the transmissivity means it is the surface property by which whatever is the incident radiation which is falling over it, a part of which is transmitted across this surface is actually known as the transmissivity. And when we are saying that we are talking about the entire range of the wavelength, and hemispherical all means all direction, so it is basically total hemispherical transmissivity. Now here we are going to talk about monochromatic or spectral irradiation. So the last case, it was total hemispherical irradiation, but now it is monochromatic or spectral. So when I say monochromatic or spectral, I am talking about a very narrow range of wavelength radiation, which is coming from all directions. So that is denoted here as G lambda. So irradiation defined above is total hemispherical property. Above means in the previous slide actually. And similarly, alpha, rho, and tau are average hemispherical properties of a surface for all directions and all wavelengths. Average here once again means total. However, for a specific wavelength, the irradiation is referred as monochromatic irradiation. And for a specific direction, the radiation is referred as directional irradiation. So what is monochromatic radiation? It is also known as spectral irradiation. It is denoted by a symbol G lambda. So it means we are talking about a particular wavelength. It is defined as the radiant heat flux. When I say radiant heat flux, what is the unit? It's watt per meter square. Because flux means per unit area. Once again, I am repeating this line. Monochromatic irradiation is defined as the radiant heat flux incident on a surface per unit wavelength interval T lambda about a wavelength lambda from all the directions. So when I say all directions, it means hemispherical. Though we are not using the term hemispherical monochromatic irradiation or hemispherical spectral irradiation. But literally it means it is nothing but hemispherical monochromatic irradiation. Okay. It is denoted by symbol G lambda and it is measured in watt per meter square micrometer. And if I take the wavelength in meters only, then the unit would be watt per meter cube. But in most of the cases, in most of the books, you will find that this value is given in watt per meter square micrometer. Micrometer being the unit for the wavelength. So mathematically, we can express it as G lambda is equal to dg. What is dg? Dg is that small amount of the energy which is falling in a particular range of the wavelength d lambda. So G lambda can be given as dg divided by d lambda. And if we want to calculate that small amount of the energy that is falling in this particular range, that would be equal to G lambda into d lambda. From this equation only, we have got this particular result. Now this is the value of dg. And if we want to calculate the total incident energy over the entire wavelength range from all the directions, then we will have to integrate this particular equation over the wavelength lambda is equal to 0 to lambda is equal to infinity. So G is equal to G lambda d lambda and its integral from lambda is equal to 0 to infinity. And it will be known as total hemispherical irradiation. So I hope this total hemispherical and monochromatic terms are clear to you. Now we are going to talk about the spectral absorptivity, spectral reflectivity, and spectral transmissivity. So alpha lambda stands for spectral absorptivity, rho lambda stands for spectral reflectivity, and tau lambda stands for spectral transmissivity. So we can either call it as spectral or we can also call it as monochromatic. So whether you call it as a monochromatic or spectral, both are one and the same thing. Now we talk about the spectral absorptivity alpha lambda, spectral reflectivity rho lambda, and spectral transmissivity tau lambda of a surface are defined in a similar manner as spectral absorptivity alpha lambda is the fraction of monochromatic irradiation absorbed. So monochromatic irradiation is what? It is basically G lambda. So here in this diagram, if this incident radiation is rather than G, if it is G lambda, means it is coming in a particular wavelength band, then a part of it which is absorbed here, which is here given by alpha, no, it's not alpha G now, it is alpha lambda into G lambda. Okay, this part is actually known as the total energy absorbed in a particular wavelength range, and this value and the ratio of this total value and this value G lambda is known as the spectral absorptivity. As you can see it here, alpha lambda is equal to G lambda alpha divided by G lambda. Now basically this term which is written here, alpha lambda G lambda, is given a symbol alpha G lambda alpha. Okay, so G lambda alpha is the basically incident radiation which is absorbed, and its value is equal to alpha lambda G lambda. So you can see alpha lambda will be equal to G lambda alpha divided by G lambda. In a similar fashion, we can say spectral reflectivity rho lambda is the fraction of the monochromatic irradiation reflected. So this value is now not, it is rho lambda G lambda, and in totality we are calling it as G lambda rho. So G lambda rho. So we call rho lambda is equal to G lambda rho because this is the total energy which is reflected out of the total incident energy which is incident on the surface or coming to the surface from a particular wavelength range. And in a similar fashion, we can define spectral transmissivity tau lambda. It is the fraction of the monochromatic energy transmitted. So what is the monochromatic energy transmitted? This is the transmitted part. Now it is not tau times G, it is tau lambda G lambda. And this value is given a name G lambda tau. So here we can say alpha lambda, sorry, it should not be alpha lambda. It is actually equal to tau lambda. And this value is equal to G lambda tau divided by G lambda. So I hope this part is clear, where G lambda alpha, G lambda rho, and G lambda tau are absorbed, reflected, and transmitted portion of the spectral irradiation G lambda. So once again, I would say that when I am calling alpha lambda, now what is this alpha lambda? It is spectral absorptivity, but I can also call it as hemispherical spectral absorptivity, or it can also be called as hemispherical monochromatic absorptivity. In a similar fashion, we can extend this term, this method for the other terms also. For example, if I am talking about the reflectivity, spectral reflectivity, I can say that it is hemispherical spectral reflectivity, and a similar manner I can call it as a hemispherical spectral transmissivity. So basically, hemispherical means from all directions, and spectral means in a particular wavelength range. So similar to the average properties, where we have said that alpha plus rho plus tau is equal to 1. 1. In a similar fashion, I can say alpha lambda plus rho lambda plus tau lambda is equal to 1. So I hope this part is clear to you. So now we are going to calculate average hemispherical absorptivity, reflectivity, and transmissivity. That means now we are going, basically now it is in a reverse fashion, we are going to calculate these values from the values of alpha lambda, rho lambda, and tau lambda. So the expressions have been derived here for calculating the value of alpha, rho, and tau from the values of alpha lambda, rho lambda, and tau lambda. So you can see it here, alpha. Now, when we define alpha, alpha is basically the incident, the part of the incident energy which is absorbed. So what is the incident energy which is falling on the surface? It is given by G lambda into D lambda. So for example, if I have to draw a curve for the incident radiation, suppose this is the curve for G lambda, okay, and this is lambda is equal to 0 to lambda is equal to infinity. So what is the total energy which is incident on a surface? And if I am considering this band of lambda, this can be given the name d lambda. Here the value of uh, incident energy, I am calling it as g lambda. So this is the total energy which is incident on the surface. So how to calculate it? I can calculate it by calculating the area of this particular rectangle, and this area will be equal to g lambda into d lambda. Now basically this value is nothing but this is equal to dg, and if I have to calculate the total incident energy on the surface, then I have to integrate this value of dg from 0 to infinity. So that is what has been done in the denominator. So this is the total energy incident on the surface. Now I want to calculate how much has been absorbed. Now you know this is the absorption part, which is not alpha g, it is basically alpha lambda into g lambda. This is the absorbed part. And if I am talking about the absorption of the surface, if I plot the graph here between the suppose this is the value of alpha lambda, and suppose it is varying something like this, and if I want to calculate the value of incident energy which is absorbed, so it is you can say this is this will not be alpha lambda, it will be, you can say, alpha lambda into g lambda. So it is varying something like this. So this value will be equal to if I am considering a particular value of alpha lambda g lambda here, so I can take this particular value of the d lambda, and then I can calculate the area of the rectangle here. So the total energy absorbed will be given by alpha lambda g lambda into d lambda, and this total energy absorbed in that particular wavelength range d lambda only. This is d lambda. Okay. And if I have to calculate the energy absorbed for the whole wavelength range, then I will have to integrate this value. So this value gives me the total energy absorbed over the whole range of the wavelength. And in the denominator, you can see it is the total energy incident on the surface. And the ratio of the two will be given known as the average hemispherical absorptivity. In a similar manner, we can extend this method to calculate the value of the reflectivity. So reflectivity will be given by rho lambda, g lambda, d lambda. This is the energy which is reflected in the wavelength range lambda by the surface, and we have to integrate it over the whole wavelength range 0 to infinity. So 0 to infinity shows that this is the amount of the energy which has been reflected by the surface in the whole range of the wavelength. And once again, this in part which is in the denominator, this shows the total energy incident on the surface. And in a similar manner, this if I write, this is basically g lambda. If I say this particular value, this is actually tau lambda into g lambda, and this part, reflected part, is rho lambda into g lambda. As I have told you that this value is actually equal to g lambda rho. So rather than writing here, this equation can also be written as integral 0 to infinity g lambda times rho into d lambda. So basically, when I'm writing, I have drawn this graph. This is basically g lambda alpha graph. Okay. So in a similar manner, we can define the transmissivity, which is given by tau lambda g lambda d lambda integrated over lambda is equal to 0 to infinity. And we can also write this term as integral 0 to infinity g lambda tau d lambda, and in denominator this part is actually the total energy which is incident over this particular surface. Now we are going to discuss about various types of the bodies. What are the various types of the bodies? One is opaque body, another is white body, and the third one is the black body. So what is a opaque body? Opaque body is, or an opaque surface, there is no transmission. Thus the reflectivity and absorptivity are given by, are related by alpha plus rho is equal to 1, because opaque body will not transmit anything. So for a opaque body, the value of transmissivity is equal to 0. And similarly, I can also extend this definition for a particular range of the wavelength or a particular band of the wavelength. I can say alpha lambda plus rho lambda is equal to 1, and I can say tau lambda is equal to 0. When I say white body means energy absorbed is equal to 0, energy transmitted is equal to 0, but energy which is reflected, that value is equal to 1. So a body is called white body, which reflects almost all radiations incident upon it and does not absorb or transmit any part of it. Now we talk about the black body. We have already talked about the black body, and you know, a black body neither reflects nor transmits any part of the incident radiation, but it is absorbing all of it. That is, rho is equal to 0, means reflectivity is 0, transmissivity is equal to 0, whereas the absorption is equal to 100%, or alpha is equal to 1. So now I am going to discuss a example. So here you can see in the diagram what we have been shown. We have been shown the spectral distribution of surface irradiation. Now what is irradiation? Irradiation is G, and when I say spectral, it means G lambda, and we can also call it as hemispherical spectral irradiation. It is known as hemispherical Hemispherical means from all directions. Hemispherical, spectral, or spectral we can also call as monochromatic. Monochromatic irradiation. Irradiation means energy falling on a surface. So you can see, if you see this particular diagram, you can see here, this is G lambda and its unit is watt per meter square micrometer. And you can see initially when lambda is equal to 0, the value is equal to 0 for the G lambda. When the value of lambda is equal to 5, the value of G lambda is equal to 1000. And this value remains equal to 1000 till the lambda is equal to 20 micrometer or 20 microns. And at lambda is equal to 25, the value once again reduces to 0. And further till infinity, this value of irradiation or monochromatic irradiation is 0 basically. So we have been asked to calculate what is the total irradiation. Total irradiation means what is the value of G basically. We have to calculate this value and the unit should be equal to watt per meter square. Okay. So what is G? G is energy which is incident on a surface which is coming over the whole wavelength range and from the all directions. So that is what we need to calculate. So what we are given with? We are given the spectral distribution of the surface irradiation. So G lambda 1 is equal to 0. This is the lambda 1. Here the value of G lambda 1 is 0. Then G lambda 2 means this is the value of lambda 2 at 5 microns. Its value is equal to 1000 watt per meter square micrometer. And G lambda 3 means the value here, this is the lambda 3. So here the value of G lambda 3 is equal to 0. And we have to find total irradiation on the surface. So how we can calculate it? We can calculate it from this particular equation. G lambda is known to me. I can multiply it by D lambda. So this value will give me energy incident in a particular band of the wavelength. And if I want to calculate it, I will integrate this equation for lambda is equal to 0 to lambda is equal to infinity. So let us see in the next slide how we can do it. So we can break it in 3 parts. For one case, we can calculate this energy. Then we can calculate this energy. Then we can calculate this energy which is incident on the surface. So basically we have a triangle first, then we have a rectangle, and once again we have a rectangle. And beyond this, up to infinity, value of the monochromatic irradiation value is actually equal to 0. So what is the total value of G? So first of all, we will integrate G lambda D lambda for the range 0 to 5 microns. Then we can integrate G lambda D lambda from 5 micron to 20 microns. Then we can integrate it from 20 to 25. And then we can calculate G lambda D lambda from 25 to infinity value of the wavelength. So now we can calculate this value. The first value here, this value is the area of the triangle. So it will be equal to half base into height. So this is height actually, and this is base, 5 minus 0. Plus the second integral is between 5 to 20 microns. It is the area of a rectangle. So the width of the rectangle is 20 minus 5, and the height is equal to 1000. And the third is half, and this is once again the height, and this is the width of the triangle. Plus the next one is 0 because it's a straight line. So you can see here it is 500 into 5, so 2500. Here it is 15 into 1000, it is 15,000. And then once again here it is 5 into 1000 into 2, so once again it is 2500. So total value comes out to be 20,000 watt per meter square. So I will end my class here. In the next class we will be discussing about the solid angle and some more properties of the radiation.